So far in the widgets package, we've done widget, we've done title because it's very simple, and we've done layout. And widget and layout kind of form the basis of everything else in this package. Kind of everything else in this package is more or less built on top of those two things. And so I'm kind of going to go up the hierarchy, if you will, from least complex to most complex. And the next step up in the least complex is panel layout. So this panel layout module builds directly on top of layout. So this is going to be basically the first example. If we recall, the layout class itself is an abstract class, so you can't instantiate it directly. You have to subclass it and implement a couple methods. So panel layout is the simplest concrete implementation of a layout. And it exists so that you can, the intent of this is you use a panel layout or a panel when you want to lay out your widgets using CSS directly, rather than using one of the other built-in layouts or your own layout that does a bunch of layout computations and all of that math in JavaScript and uses absolute positioning. There are definitely going to be times when using a standard CSS layout is appropriate, and you need a way to do that in Phosphor, because if we recall, the only way to add child widgets to a widget in Phosphor is to put them in a layout. So the panel layout is the answer to that. It allows you to add child widgets to another widget and actually arrange them and lay them out using CSS. So this is a very simple concrete class, and it doesn't do any of its own math computation. It delegates all of that to CSS, but it does handle the passing of messages, and it fulfills that messaging protocol to ensure the messages get proxied up and down the tree. So we'll go through this first, and a pattern that we follow in Phosphor quite regularly when we talk about making layouts is you'll see a class, for example, named panel layout, and then you'll see a widget named panel. Conversely, you'll see a layout called like split layout, for example. Then you'll see a class called split panel, and they're basically the counterparts of one another. So in the case of, let's just say you want to have like some empty Phosphor widget that you throw a bunch of child widgets into, and you want to arrange them with CSS, and you don't really care about what's public API and what's private API and all of that. You don't have to use panel layout yourself directly. You'll be able to use the panel widget, and I'll describe that class next. But basically, there's always going to be a sister counterpart to a layout in the Phosphor widgets package. So panel layout has a panel widget counterpart, and that'll kind of, how those tie in will make more sense when I go over the panel widget itself. But anyway, so moving on with this, we see we implement the dispose method, or I should say we re-implement the dispose method on the panel layout. And what this does is, this is how the child widgets for, so if we recall, when you dispose a parent widget in a hierarchy, you expect all of the child widgets that it owns to also be disposed. And this is an example of the implementation of that. And so what this does is it basically says, while we've got widgets that are children of this panel layout, or while this panel layout owns widgets, it pops the end of that widget, it pops those widgets off, and then calls dispose on them. And then it calls the super dispose method. Now, a question you might immediately be asking yourself, if the layout base class defines an iterator protocol, and every layout implementation must implement that iterator protocol, and when you iterate over a layout, it yields all the child widgets of the layout, why then doesn't the base class take responsibility for disposing the widgets? And I'll give you an example. I'll open another tab here just to kind of point out what I'm talking about. So if we go back and look at the layout base class right here, why does this base class method not iterate over all of the child widgets, since it has this iterator protocol down here, which is an abstract method, and dispose of all the child widgets? And the answer to that is because the base class layout doesn't actually know how the subclasses are storing the child widgets internally. It doesn't know how they're storing it as an actual stateful attribute. And in this case of the panel layout, they're just stored, the child widgets are stored in an array. And so the base class would have no way to clear the internal state of its subclass when it goes to dispose of all of these child widgets. And since ideally we don't try to dispose a child widget more than once, we don't want to rely on iterating over some child widgets and then calling dispose, which could be an arbitrarily complex method, which goes back and may, somehow call back into the dispose method on the panel layout. So things can get kind of wonky there when you don't have control over the state of how the children are stored. So all of that to say is that anything that inherits directly from layout is responsible for disposing the child widgets, which it owns in its dispose method. And so that's what this little while loop is doing right now. And it's doing it a safe way. So instead of iterating over the array, which might be, somebody's first instinct to just kind of do a for loop over that array of widgets, dispose all of them, and then set the length of the array to 0. Again, that's not entirely safe because the actual act of calling a dispose method on a widget could trigger arbitrary code execution, and we don't know what that's going to do, whether it's going to add more children to the layout, whether it's going to remove some children from the layout, or other things. So the safest way to do this is to what we see here, which is while there are still child widgets in the array, you pop off from the end and dispose that child. When that's all done, then you can call into the superclass method to do the disposal. And again, we're following the same pattern that we follow on all the iDisposable interfaces. When you re-implement the dispose method, you do whatever work you need to do in your subclass, and then the last thing you should do is call the parent classes or the superclasses dispose method. Okay, moving on. We provide a read-only getter, which provides a view into the array of widgets which are contained with the layout. So in case somebody has wants to actually iterate over these widgets by index or do whatever they need to do and don't necessarily want to use the iterator interface, we do provide this extra read-only getter, which exposes that internal state as a read-only array, so it can't be modified directly. Then we go through and implement the iterator or iterable interface that's required of the base class. This is very simple. This is just using the built-in iter method in Phosphor algorithm package to create an iterator around an array of objects. And then we go through and we start with the actual public API of this class panel layout. So if you recall, the base class layout doesn't have any sort of API about, doesn't define any sort of abstract public API about how you should add children to a particular layout. Because, for example, a panel layout might do things by index. They might be ordered widgets, but something like a dock layout, for example, or a dock panel layout, there's not going to be some canonical ordering to the widget. So it wouldn't make sense to have an index-based API to add or insert widgets into the layout. So it's actually, that responsibility is delegated to the actual concrete implementations of the layouts to define their own public API in a way that's appropriate for them for adding or inserting child widgets into the layout. In the case of the panel layout, it's done by index. So there's a convenience method to just add a widget to the end of the layout. It just delegates to this insert widget method, which is kind of the workhorse, where you insert a widget at a particular index and you give it the child widget. So if we go through the actual logic of this, this is all documented quite well. We try to also document any kind of undefined behavior. In this case, the undefined behavior, if you call insert widget with an index, which is not an integer number, then the behavior is undefined. This wouldn't be a problem if we had a little bit more type safety and numbers in JavaScript. You actually had floats and ints and that kind of stuff. But we don't, so don't pass a non-integral index. Okay, so the first thing we do is we take the widget that we're inserting into this layout and we reparent it. So in this case, this.parent for the layout is either going to be the parent widget, which is going to own the layout, or it's going to be null because the layout has not yet been installed on the parent. In either case, this widget is going to be reparented. It's either going to be parented to the new parent, which is going to own it, or it's going to be set to null and removed from that layout of wherever it was before. Then we're going to see if the widget perhaps already exists in the layout, because if it does exist in the layout, what we want to do is just move it into the current location, or instead of actually inserting it into the array. So we look up for the index to see if it exists or not. Then we clamp it to the bounds of the array, so we're not indexing out of bounds. And if the widget does not already exist in the array, then we go ahead and we insert it at the computed location. And if the layout is parented, so if this what do you call it, panel layout is already associated with a parent widget, then we go ahead and we call this overridden method, or this method down here, which is a protected method called attach widget, and we'll see why this becomes important a little bit later. Then we call this method attach this widget at a particular index, and then we give it the widget. Otherwise, the widget already exists in the array and it should be moved. So we do a little bit of logic there to adjust the index as appropriate. We test to see if we're trying to insert at the current index where it already exists. If we do nothing. Otherwise, we move the location of the widget in the array. And then if the layout is parented, we also move the widget in the DOM to the appropriate location. So the thing to notice here, I'm always checking before I do something if the layout already has a parent. And if the layout does have a parent, that means that the DOM node that is associated with the child widget is going to be inserted to the DOM node associated with the parent widget, which makes sense. If there's no parent widget yet, then calling either of these methods doesn't make sense, because these methods, when we get down to them, you'll see this is actually intended to attach the DOM node of the widget to the parent's DOM node, and this is intended to move the DOM node of the widget in the parent's DOM node. If there is no parent yet, that doesn't make sense, so we just bail. And then later on, once this layout finally gets installed on the parent widget, you'll see that there's logic to make sure that all the DOM nodes are put into the correct place. Next method is the remove widget method. Now, if we recall, this is an abstract method defined by the base layout class right here. So this is required because you need a way to remove widgets from a layout. If we recall, the normal way to remove a widget from the hierarchy is to set its parent to null. However, if you've added a widget to a layout and you have not yet installed that layout on the parent widget, then the child widget doesn't have a parent. Its parent is still null. So setting it to null will do nothing. So you have to have a way, just to be a complete API, to remove a widget from a layout if it doesn't yet have a parent. And so we have to have this abstract, remove widget method. And so in the panel layout, this is the implementation of that. And it's just a very simple, it delegates to another public API where it's removing a widget at a particular index and it's finding the index of that widget. And that's the method right below here. So this method removes a widget at a given index from the layout. And we see in the notes that a widget is automatically removed from a layout when its parent is set to null. This method should only be invoked directly when removing a widget from a layout which has yet to be installed on a parent widget. So again, that's basically another explanation of what I just said. So usually you're never going to be calling these methods directly. It's going to be a very, very rare case when you have to do it. Typically, these methods are called automatically at the appropriate time in response to you, the user, setting the parent of a widget to null. Okay, so the first thing we do is...
Hey, Chris?
Yes.
So when you set the widget's parent to a null, I guess that releases a signal, right, to the parent to let the parent know.
It sends a message, actually.
Message.
Okay. A signal. So we use. So the nice thing about sending messages is there's no overhead for subscriptions, memory overhead for subscriptions like you have with signals. And if we recall, the signaling pattern is a one-to-many relationship. So you have one thing trying to notify perhaps many observers. Whereas the messaging pattern is a many-to-one. So you may have several different things that want to send a message to the same thing. So it's kind of the inverse pattern. And one of the advantages of the messaging pattern is that, like I said, it doesn't require any storage overhead for sending messages. So if we look here in this parent setter, so this is the widget module. So this is in the widget class. And if you set the parent to null, right here, and that widget has a parent, and that parent is not disposed, then it will get a message. I mean, this is just happens if you change the parent. So whether you're going from any parent to null or any parent to another parent, whatever, the old parent still gets this message that says child removed.
Right.
And eventually that message is going to propagate to the layout that's installed on that parent, and that layout will then handle that. So if we go back to this layout-based class, eventually that child removed message is going to come in through this process parent message method right here. And it's going to call this protected method, which is on child removed, which is down here at the bottom, which will then eventually call the remove widget method on your behalf. So this is why you don't typically ever have to call remove widget yourself. And the proper way to do things is just set the parent to null. And that's typically always going to work.
Okay, so then when the layout does not have a parent, that's when you need to call the remove widget method directly, right?
Correct. And that's typically never going to happen, right? Because you'd be like, why would you add a bunch of stuff to a layout just to then remove it?
To remove it, yeah.
Yeah. So.
Okay, I think that clears it up. Thank you.
Okay, so this array ext, this is a namespace in the Phosphor algorithm package, which has some methods that probably should exist on the built-in JavaScript array, but don't. And in this case, we remove a value at a particular index. And if that index is out of bounds, then this is going to be undefined. So we check first, we say, the widget's not undefined, and we have a parent widget. That means that the DOM node that's associated with this child widget is currently installed on the DOM node that's associated with the parent widget, and that needs to be detached from the DOM in order to be consistent, because you don't want to remove a child widget from a parent but leave its node in place. So that's where we go through and we detach the widget from the parent. And this is calling into a method that's protected on this class that we'll get to in just a couple seconds. Okay, moving on. Now we're getting into some more overridden protected methods that are defined by the base class, the base layout class. So this is the init method, which is also defined in the base layout class. And if we recall what that one does, so this method performs layout initialization, which requires the parent widget. So this method is automatically called when the layout is installed on the parent widget. And if you think about why this is necessary, if you think about the way that layouts are used, typically you're going to do something like create a box layout, add a bunch of widgets to it, and then set that layout onto the widget the parent widget that you care about. So you've instantiated the box layout, then you've added a bunch of widgets, and then you install it on the parent widget. At the point that you install it on the parent widget, you need to do a bunch of things. You need to make sure that all of those child widgets are reparented to the parent widget. You need to make sure that all of those DOM nodes for all of those child widgets are added to the parent DOM node, and whatever other state initialization needs to be done by any of the subclasses. So you've got really a two-step initialization process. One that can be done just in the beginning when you instantiate the class, and another one that requires the parent widget as context. So the framework will automatically call this init method on your layout when that layout is installed on a parent method or on a parent widget. And since a layout can only be installed on a single parent widget during the layout's lifetime, we know that this init method will only be called once during the lifetime of the layout. So what the base class does is ensures that all of the child widgets are parented to the new parent. The panel layout goes one step further in its reimplementation. The first thing it does is it calls the base class's init method so that all of those children get parented appropriately. And then it goes through and iterates over the child widgets by, basically by number. So one of the features of this Phosphor iterator function, where this function which takes an iterator or an iterable object and acts like the for each method on a JavaScript array, gives you the object that you're iterating and the current index of the iterator. So we go through and we attach all of the DOM widgets for those children to the new parent DOM widget. So that's what this init method does. Should make sense why that's necessary at this point. So getting into the next three methods, which are attach widget, move widget, and detach widget. And this is basically these are basically the workhorse functions which actually manipulate the DOM. So everything we've talked about up until this point with widgets and layouts, if you've noticed, have had absolutely nothing to do with the DOM or any nodes. It's all dealt with widgets as basically just JavaScript objects. So finally, what we've been able to do with the way that this subclass is defined is encapsulate all of the basically all of the DOM manipulation for this layout is encapsulated in 3 methods, which is attach widget, move widget, and detach widget. And basically what they do is that attach widget inserts the child widget's DOM node into the DOM. Move widget moves the child widget's DOM node in the DOM, and detach widget removes that child widget's DOM node from the DOM. So we'll go through them kind of one at a time and see how that goes. And we'll see why they're named attach, move, and detach. And it's related to the messages that these methods end up sending. So let's take a read through the documentation here. So attach a widget to the parent's DOM node. Takes 2 parameters, which is the current index of the widget in the layout, and the child widget, which needs to be attached to the parent. And it says this method is called automatically by the panel layout at the appropriate time. It should not be called directly by user code. That's true. And this is unequivocally true. You will never actually call attach widget yourself, and you won't call it from your subclass, and you won't call it obviously from not a subclass because it's protected. The default implementation, when you see something like this, the default implementation, this is a phrase that I use all over the place, and it means that this method is intended to be overridden or re-implemented in a subclass if that's necessary for the behavior of the subclass. And it is in fact re-implemented quite often in some of the other layouts that derive from panel layout. So the default implementation adds the widget's node to the parent's node at the proper location and sends the appropriate attached messages to the widget if the parent is attached to the DOM. So it sends the appropriate attached messages. This is why this method is called attach widget. And it says subclasses may re-implement this method to control how the widget's node is attached to the parent's node. Makes sense. Okay, so in this case, the purpose of the panel layout is to just manage this sort of behavior and to make sure that the child widget's DOM nodes are inserted at the correct location in the parent widget's DOM node. Since the panel layout itself is index-based and a widget has an index and an ordered location in the layout, it also makes sense that the actual DOM nodes that belong to those child widgets follow the same ordering in the actual real DOM, in the DOM tree. And so the way that we do that is we have to leverage the insert before method or the insert after method of the DOM. And so to do that, we need reference nodes because the DOM itself is not index-based. It's actually a tree of doubly linked nodes. It's kind of neither here nor there. Just know that the DOM itself is not index-based, but this API is. So we have a couple methods here to convert from one to the other. So what we need to do is we want to insert at a particular index. So we need to look up the next sibling reference node because we insert before a node in the DOM, not at a particular reference. So the first thing we do is first, we know that since attach widget is being called, we know that we have a parent widget. So we don't have to check whether this.parent is null. We can just null assert there. And we can grab the node at a particular index. And this is actually an interesting thing with the DOM is that you can index this children's list object of DOM nodes by index, but you cannot insert by index. So it's just a bit of a idiosyncratic API, in my opinion, but it is what it is. So anyway, we can look up what will be the next sibling node by index, and that becomes our reference node. And then we check to see if the parent itself is attached to the DOM. And if the parent itself is attached to the DOM, then we need to go ahead and send a message to that child widget that it's about to be attached to the DOM because we're actually about to insert its DOM node into the DOM tree. So this is where this layout is fulfilling part of the messaging specification, if you will, of widgets to make sure that this child widget knows that it's about to be attached to the DOM. Then we go ahead and we insert that node before the sibling reference that we just looked up. And again, we can null assert because we know we have a parent. And then we check again to see if the parent is still attached to the DOM because remember that this sending message is basically allows for arbitrary code execution. And as a result of that, we don't know. We cannot assume that we are still attached to the DOM or that the parent is still attached to the DOM. So we have to check again. And if the parent is still attached, then we can go ahead and we can send that after attached message to that child widget to let it know that it's been successfully attached to the DOM. Alrighty, moving on. We're going to see that this method, move widget, which moves a widget in the parent's DOM node. And if we recall where this is called from, I'm just going to do a little Control F here. So if we get to this point on insert widget, where the widget already exists in the array and should be moved, this is where this method is called from. So in this, if you want to move a widget in a panel layout, you just try to insert it again at the whatever index you want it to be. So rather than have a dedicated move widget method that you have to call, then that tries to detect whether it's already inserted and throws an exception or something like that, we just made it a simpler API. So if you want to move a widget, you just insert it, always just insert the location you want it to be, and this framework will automatically detect if it's an insert, if it's a real insert, or whether it's just a move. And if it's a move and we have a parent, then we go ahead and we call this move widget method. The first thing we do is we check to see if the parent is attached to the DOM. And if we do, we need to tell this child widget that it's about to be detached. Now, the reason for this is actually important, and it has to do with how browsers, some browsers have implemented moving a widget in the DOM, and particularly in Chrome. I had to go look in the source code of Chromium to find out where this was happening, because some browsers will actually move a node in the tree without actually setting its parent node to null or taking it out of the tree in the process or whatever. Chrome doesn't do that. So if you actually try to move a widget in the DOM by inserting it at a new location, it is implemented as removing it first and then inserting it in the new location. And that does have an effect based on what DOM observers that you might have going on, or what other kind of side effects you might be trying to observe in the browser and various browser behaviors and what that sort of thing. So because that actual moving behavior was not consistent across all browsers, I opted to implement moving by actually removing the DOM node and then inserting it again, because that's the only way to get all the browsers to behave consistently and not having to special case Firefox or Chrome or any of that kind of stuff. So since we implement move as a remove and then an insert, we have to let the child know that it's about to be detached from the DOM. So that's the first thing we do. The next thing we do is we have to remove that child's node from the parent. And again, because this message could have arbitrary code execution, we have to check again if the parent's attached. Then we have to tell the widget that it's been detached. Now we go through the same insert behavior again, and we look up the new reference node, and basically all of that insert logic occurs. So in the case of moving the widget, it's literally the logic of remove widget, then the logic of insert widget. And I've just done it in line to make it a bit more, I guess, self-contained, rather than unequivocally relying on attach widget and detach widget to do the same thing in the case that subclasses have overridden one but not the other, etc. So this was just the safest way to implement it when you consider all the factors involved. And then detaching widget, basically the documentation is the same logic as above, just inverted in terms of its behavior. We know we're about to detach the widget, the child widget, so we have to send it that message. Then we go ahead and remove that node from the DOM, and then we send it the after detach message. And then if we look at all the state that is held by layout, it's exactly one array. So lots of behavior, very, very little state overhead, literally just one array of widgets. So you can create panels and panel layouts till the cows come home, and it's not going to affect really the memory consumption of your app. Now, the sister class to the panel.
Actually,
yeah,
can I ask you a question? So,
yeah.
So when you move a widget, you will receive, if you're a child widget and that you're being moved, you'll receive a before detach and you'll receive an after attach. Is that right?
If you're a child widget and you've been moved, or you are being moved, you will receive 4 messages. You'll get a before and after detach and a before and after attach.
Okay, right. So then I guess this underscores that treating the protected methods that you probably overwrote, the on after attach, on before detach, you shouldn't treat your detachment as though you're gonna go away, right? So it doesn't, like, it's not, the life cycle allows for plenty of movement within the DOM. So those signals sorry, those messages don't mean you're going away. Is that a fair characterization?
Yes, that's entirely correct. Yeah.
Okay.
Because especially when you start talking about like the context of a drag and drop app where you're dragging widgets from one parent to another, like they're going to be detached and then attached however many number of times as you're being drag and dropped around the app. Especially if you're going from like, in the case of a dock panel, you're not actually changing parent widgets, but in the case of dragging and dropping between widgets, you are. So it just depends. Yeah, there's definitely cases where, you might be detached and then attached again, and then, yeah, you really don't know that you're going away until you've been disposed. Just a little side note here. If we go look at some of the naming conventions of these modules, we see split layout and split panel, stacked layout, stacked panel. What else do we see? Grid layout. I haven't made a grid panel yet. I should probably do that. We have dock layout and dock panel, box layout and box panel. I didn't want to do panel layout and then panel. That would have been weird. So it's just panel layout and panel. So I kind of had to break with naming inconsistency just because it made sense there. But so the basically the sister class for panel layout is panel. The sister class for everything else, foo layout, for example, is foo panel. So this is the only deviation from that naming scheme. Sorry, I couldn't think of anything better. It was more consistent. It does irk me a little bit, but I think the alternative would have been terrible. So, okay. So what these sister classes are nothing but convenience classes that wrap a layout. And they wrap the layout. And by what I mean by wrapping the layout is you've got this public API, for example, defined by panel layout, which is, you've got this read-only getter to show the widgets. You've got this add widget method. You've got this remove widget method. You've got this remove widget at, etc. Those are convenient methods that you might want to be able to call, and you might want to just create some kind of parent widget that's a panel, add a bunch of children to it, and then be done with it. You don't really care, or based on the context of where you're using that parent widget, that nobody else is going to be able to manipulate it out from under you. So it becomes convenient to have just a single widget that wraps that layout for you and delegates all of those public APIs so that you're not actually having to create the layout yourself and deal with it. It would be nice, for example, if I could just say new panel and then add a bunch of my widgets to it, like a tab bar and whatever else I want to do, lay it out with CSS and call it done, and not have to worry about layouts at all. So that's what these convenience wrapper classes do for you. So it's a simple and convenient panel widget class. This class is suitable as a base class for implementing a variety of convenience panel widgets, but can also be used directly with CSS to arrange a collection of widgets. And so this class provides a convenience wrapper around panel layout. So if we see how it's implemented, it's real simple. Take some options, which we'll get to in a second, but then it follows the same convention as all Phosphor widgets and adds a class name to the widget so you know where it came from. And then it preemptively creates and installs that layout for you. Now, notably, this layout's going to be empty. There's going to be no child widgets associated with it. And it's totally fine. The way that the layout API is designed is it doesn't care if you create a layout and add a bunch of widgets to it, then install it on the parent, or you create an empty layout, install it on the parent, and then add a bunch of widgets to it later. The former is a bit more efficient in terms of processing power, but it's really not going to make that much of a difference in practice. And so for convenience purposes, it's fine to do it either way. So the layout's created for you. And here is where we find the first real example of why you're not allowed to change a layout at runtime. So if we remember that this setter is a public method, but if we look at this API that the panel widget is trying to wrap, it needs to assume that its layout is a panel layout. And if we go back and we look at the actual getter, the type definition for this getter right now, this layout attribute, it's typed as a base layout class. Well, the base layout class doesn't have a .widgets method or a .widgets property. So we have to do this cast. And if we could not assume that this .layout was a panel layout, we'd have to do some expensive instance of checks, and then the API would get weird, and then this type definition here would be unsafe. And so everything just became easier by saying once you install a layout, it can never be changed for the lifetime of the widget. That allows us to preemptively set the layout in the constructor and then assume everywhere else in this class that the layout is going to be an instance of a panel layout. And since we can do that, this cast is actually safe. So it's a raw cast, but it's a safe cast because we know that the layout can never be changed. So that right there is the sole reason, I guess not the sole reason, but a pretty big driving reason for not being able to change the layout after it's been set on a widget. So at any rate, moving on. So the panel class re-exposes that read-only array of child widgets. It re-exposes the add widget method, and it re-exposes the insert widget method. Notably, it does not expose the remove widget at method, which is defined on the panel layout right here. And it also doesn't expose remove widget. And the reason is because if you've added a widget, a child widget, to this panel, it by definition has a parent widget. So there's no need to use those methods. You should just set the parent widget of that child to null in order to remove it from the layout and to remove it from the panel. So that's why those methods are not exposed. It basically forces you to do the right thing. So if all you want to do is have a collection of widgets inserted into a parent widget and you want to layer it out with CSS and you want to slap it on the page and be done with it, the panel class is a great way to do that. You don't have to do anything fancy. You can create a panel. You can add your own CSS class names to it. You can give it an ID. You can tag it however you want, so you can style it with CSS, add in a bunch of child widgets or insert them at whatever location you want, style those with CSS, and everything's handled for you. So all the resize messages will propagate appropriately. All the attach and detach methods will propagate appropriately. All of that complex behavior has already been handled for you by the panel layout and by the base classes. So your job as a user of the API is very simple. And so I think at this point, we've seen these classes like the widget-based class, the layout-based class. Now we've seen a layer on top of that, which is the panel layout and the panel. And that kind of shows the level of API granularity that we can achieve with Phosphor. You can go very, very low level and you can implement your own layout class and you can implement your own widgets, or you can use the ones that are predefined for you, which have very high level APIs and do a lot of that work for you. So if you need something simple and high level, you have it. And if you need to peel away a layer of that abstraction, basically there's multiple layers of abstraction. And if you need more control, you can always peel away one layer of abstraction and get more control. In this case, the first layer of abstraction or the top layer of abstraction would be the panel widget. If that's doing too much for you, for example, let's say you want to use a panel layout because you do want to use CSS to control the layout of your children. However, you don't want these methods, add widget and insert widget, to be exposed because your widget is meant for public use and it's got its own public API, and you don't want people to be able to add their own child widgets to it. What you do then is you create your own widget class, your own widget subclass. So instead of using panel, you're going to, class, my foo widget, whatever, extends widget. And then in your own constructor method, you can create your own panel layout and install that. And you simply don't have methods like this. And since you own the layout and the base layout class itself has no way of adding child widgets to the layout, it's a completely safe API. You don't have to worry about other people coming along and adding their own child widgets to your widget, or disturbing some assumptions you had or anything like that. So that's removing one layer of abstraction. If you don't like the panel layout, for example, and you need to do something different, you can remove that layer of abstraction and create your own layout subclass, et cetera. And so you can go all the way down to the core base classes and implement your own stuff if you need that level of control. Moving on, the options for creating a panel. And there's one option you could have for creating a panel layout, and it's the panel layout to use for the panel. So maybe in a subclass, for example, which we'll see when we get, I'll just take an example, a box layout, for example, is a subclass of a panel layout. But a box panel, for example, is going to want to use a box layout, not a panel layout. So in the case of the box panel class, which subclass is this panel class, in its constructor, it will create a box layout, which is a subclass of a panel layout, and then it will pass that along to the superclass as an option so that its layout gets used instead of creating a new just empty panel layout. That'll make more sense as we get to that class, but know that this is what that's why this option exists. It's so that base classes can customize what kind of panel layout is being used for this superclass. And then we've just got a private method, which allows me to basically have this a nice, clean one line of code here to parse out all the options and create the layout without having that parsing logic clutter up the readability of my constructor. And so basically this create layout method, it just checks to see if that options object has a layout on it. And if it does, it uses that. Otherwise, it creates a new panel layout. So pretty simple. Okay, I'm actually going to go over this module. So this module is called Box Engine. And I basically just took the name straight from Qt, which also calls it a box engine or a grid engine or something like that. This is the actual logic that does a lot of our absolute geometry computation. This module has no imports, there's no external dependencies, so it doesn't depend on widgets. It's basically just a math module. And what it does is it's an algorithm that tries to fairly appropriate space or fairly apportion space to child things, in this case box sizers, based upon a couple of criteria. Their size hint, which is basically a suggested size for a particular item, the absolute minimum size allowed for an item, the maximum size allowed for an item, what its stretch factor is, so how much that this basically this item can stretch relative to its siblings, and then a couple of other public things and so basically this is just a class that's all public properties, and this is done entirely for performance reasons. So the size is basically an output parameter of a sizer, and done is an internal flag. They're all made public so that the box engine itself can access them. So the sizers themselves are something that's created by the user of the box engine, and they're kind of passed in. We'll kind of see how that works. But it needs basically needs space in order to store computed sizes in its own flags. And since the sizers are allocated up front by the user, rather than the box engine allocating more storage space in an array for an iteration of the algorithm, we're basically allocating this size and the space to store this temporary data up front, and it's just stored on the sizer. So if you were writing a program in C, this will look very, very familiar. This is typically how you would do it for maximum performance. And I've done it this way here precisely for that reason. And this was all done based on, prolific profiling of the performance of this thing. So those do make a difference. At the end of the day, the things you care about are input parameters are the size hint, which is the suggested size, the minimum size, the maximum size, and a stretch factor. The output of the computation is the size property, and this done is an internal flag. That changing the value will have no effect. So you just pretend it doesn't exist. It's just purely for the internal storage algorithm. So typically how this is used is the algorithm works in one dimension. So it takes an array of sizers and some allowed space. So this would be like, I've got 5 widgets in a row, and I need to compute what their widths are going to be based on fitting them into a 100 pixel area or 1,000 pixel area or something like that. So the input to the algorithm is going to be an array of your 5 box sizers, which represent your widgets in that dimension, in the dimension of width. And then you're going to call calc, and you're going to give it the computed, the allowable space. So the size, so let's say I've got a box layout that has 5 widgets in it. I'm also going to have an array of 5 sizers, or an array-like object of 5 box sizers, which represent those widgets, or the widths of those widgets. And I know that I need to lay it out in 1,000 pixels, for example. So the way that I do that is it's called boxengine.calc, give it the sizers, give it the allowable space, and the output is going to be that size property. The size of each sizer is updated with the computed size. And what it returns is some potentially useful information, which is the delta between the provided available space and the actual consumed space. The value will be 0 if the sizers can be adjusted to fit, negative if the available space is too small, and positive if the available space is too large. So the reason that this is possible, the reason that you can have a delta, let's say that you've got 5 widgets whose minimum width is 300 pixels. That means you need at least 1,500 pixels to lay them out because they have a minimum width. If you try to tell me to calculate the size of each of those widgets and fit them into 1,000 pixels, I can't, because that violates their minimum size. So you're going to get back the delta between that 1,500, which is required, and the 1,000 that you have available, and you're going to get basically negative 500 as the result. So it's a check on whether or not you have enough. This space is actually large enough to accommodate widgets given their constraints. And it's a very easy number to compute. That's why it's given back to you. It's basically free. So I return it because it's useful information. So at this point, the documentation of this one method, I think there's only 2 methods in this namespace. 3. Okay, we'll see where they're used. So the documentation is pretty thorough in terms of describing the algorithm. So I guess we'll just go through it step by step and then see that actual implementation in code. So what this calc method does is it calculates the optimal layout size for a sequence of box sizers, distributes the available layout space among the box sizers according to the following algorithm. The first thing we do is we initialize the sizer's size to the suggested size, which is its size hint, and compute the sum for each of the size hint, the minimum size, and maximum size. So what that means is that we're going to take how much space you've suggested that we're going to need, the minimum required space, the total minimum required space, and the maximum total required space. If the total suggested size or the total size hint equals the available space, we return because we're done. We're saying, you know, hey, I suggest all of these items be 500 pixels, and I've got 2,500 pixels of space. Well, size them all to 500 and be done because that's an exact match. If the available space is less than the total min size, minimize all of the sizers and return the delta, which also makes sense. If you tell me that I don't have enough space to fit all of these things, then the best I can do is size them all to their minimum size. Conversely, if the available space is greater than the total max size, the best I can do is maximize everything and return. Now, the other 2 conditions are where it gets a little bit complicated. If the layout space is less than the total amount of suggested size, so if we have less than what you suggest we should have, then there's basically less space than we would like to have, so we need to shrink some widgets smaller than what you've suggested them to be. So we shrink each sizer with a stretch factor greater than 0 by an amount proportional to the negative space and the sum of the stretch factors. That's just basically saying you've given me a bunch of sizers and you've told me how each of them should stretch or shrink relative to its sibling. I need to compute based on how much space I need to remove from this algorithm, and I need to apportion that negative space, if you will, proportional to those stretch factors. And if one of the sizers reaches its minimum size, then it has to be removed from the computation, and the computation continues until all of that negative space is consumed. And then finally, we have if after adjusting all of the sizers that can be stretched, so this is stretch factors greater than or equal to 1. Basically, what this is saying is that we're special casing sizers that have a stretch factor of 0. And what that means is that if it has a stretch factor of 0, you might think that it shouldn't be stretched, which means either expand or shrink relative to its siblings. And that's true. We're basically special casing stretch factors of 0, and they will not be resized unless it's absolutely necessary because all of the other siblings have either reached their maximum or minimum size. So where you see this quite often is in the main layout of Jupyter Lab. So if you've got both, let's say if you've got both of these sidebars on Jupyter Lab open, so we know that you've got your file browser and a bunch of other stuff on the left, then you've got your main doc panel, and then you've got another sidebar that you can expand and collapse on the right. Those areas that represent the sidebars have stretch factors of 0. That's why when you resize the browser window, either expanding it or shrinking it in Jupyter Lab, only the dock panel actually expands and shrinks. The sidebars stay at whatever size you have them set at, using your split handle. And the reason that happens is because they have stretch factors of 0, whereas the dock panel in the middle has a stretch factor of 1. So it is preferentially expanded and shrunk before either of those side panels. Now, if, for example, we set a maximum width on that center dock panel to say 1,200 pixels, and then you resize your browser quite large in width, then those side panels would start expanding once that panel hit its 1200 pixel maximum size. Because they have a stretch factor of 0, they're still allowed to expand, but only if nothing else can expand to take up that space. Okay, and then number 6 is just the inverse of that. So this is, number 5 is if there's not enough available space, and then number 6 is if there's too much available space. It's the same logic, just positive extra rather than negative extra. Okay, and then we basically have the implementation of that algorithm just defined in code. We bail early if we don't have any sizers. Obviously, just take the simple out if you have a simple out. And then we basically compute those totals that's described in the first step. Now we do our first check. Is it the available space? Is the total suggested size? We do nothing. If the available space is less than the minimum available size, we set the sizer to its minimum size, and we return. The opposite of that is if we have too much space, like if our total space is greater than the total maximum allowed size, set each sizer to its max size and return. Now here we have those two other cases. So this is going to be case number 5, and then this else is case number 6. I'll probably only do one because one's just the inverse of the other, dealing with positive space versus negative space. Okay, and we got a little bit of logic here. The loop below performs sub-pixel precision sizing. A near 0 value is used to compare instead of 0 to ensure that the loop terminates when the subdivided space is reasonably small. I was originally just comparing exactly to 0, but because JavaScript numbers are actually floats, they got a little bit wonky and sometimes wouldn't terminate, so we had to go with a near 0. So if the available space is less than the total size, first we find out how much free space we have. So this is going to be a negative. We need to remove space basically from these things. So you can think of it as negative free space, but we'll keep it as a positive number. So if we remember this space, this is an argument that's passed in. So this is the user saying, lay out all these sizers in this given amount of space. So going through this, it's like while we have sizers that have a stretch value greater than 0, and while the amount of free space that we still have is greater than 0. So what we're trying to do here in this double loop is fairly allocate that amount of space to the sizers that have a stretch count that are basically stretchable, where their stretch factor is greater than or equal to 1. Now, while we're apportioning this space, if we recall, we might try to size something less than its minimum size. If that thing is less than or equal than its minimum size, it should be sized at its minimum, and it no longer takes part in the layout. So that's why we have this double loop. So the first thing we do is we set up a variable which is keeping track of the space that we've distributed. So this is the amount of free space that's still outstanding to be allocated. Then we also keep track of how much the total stretch factors are that are still outstanding. So let's say I've got 3 widgets. One has a stretch factor of 1, another one has a stretch factor of 2, and another one has a stretch factor of 3. That's a total stretch factor of 6. So we keep track of what that total is so we can basically do that math where we can basically divide apportion the stretch factor of a particular sizer based on how many siblings it has that also want to stretch. And so we need to keep track of this, because once we remove a sizer from the layout computation, the amount of stretch factor, if you will, stretch total that needs to be distributed is less. So we iterate over all the sizers. If we find a sizer that it's already done, it's already removed from the layout, so we don't have to care about it anymore, or its stretch factor is 0, we just skip it. Rather than try, and again, this is rather than try to filter. If you read some canonical JavaScript code, somebody's inevitably going to write an array that just basically filters for sizer.done or sizer.stretch equals 0 or whatever. Well, what that's actually going to do is allocate another array. Like that's going to be allocating a temporary array inside a loop that has costs. That's going to start thrashing your GC. And remember, this algorithm is going to be called, this particular boxengine.calc function is going to be called every time you resize a widget. So in the case of Jupyter Lab, when you're resizing something at the top level of the window, like some handle on a box panel or one of the side panels or something like that, you might cause lots of box widgets or box panels somewhere nested deep in the hierarchy to resize. And every time any one of those is resized, this algorithm, this boxengine.calc, is going to be called. So this function needs to be as fast as possible, which means it should be allocating memory. And in fact, there is no allocation, heap allocation, I should say. There's some constant stack allocation that's done, but there's no heap memory allocated when this function is called at all. And iterating over an array to check a flag is extremely fast. So we don't need to try to take some premature optimization by filtering out things as they're done. We just skip them and we just iterate over the array each time. It's much faster than if I were to be doing temporary array allocations on the heap or something like that. So we skip sizers that we're done checking or where the stretch factor is equal to 0. Now we compute the amount of space that we need to remove from that sizer. And that computation is its stretch factor divided by the total amount of stretch factors that were remaining. That gives us a proportional stretch factor. And then we multiply it by the space that's remaining to be distributed. So that gets the amount of space that this sizer should take up on this particular pass of the loop. Now, we check to see if the current size of the sizer minus that amount, because we're removing space in this case, not adding it, is less than or equal to the minimum size. If it's not, that means that we can shrink the sizer by the computed amount and still not blow past this minimum size. Let's take that case first. That's going to be the else clause, and that's very simple. We simply subtract the amount of space from that sizer size, and we subtract that amount of space from the total amount of free space, because we're tracking that as we go along. So that's the very simple thing. We can shrink this sizer. We're not blowing through any limits or any minimum or maximum sizes. So just subtract the size and keep track of the free space. If we can't do that, and we're actually going to blow past the min size, then what we actually need to do is take away as much as possible that gets us close to that amount and keep track of that. So, and we need to remove that sizer from the layout computation. So the total free size is going to be the actual, whatever the current size is, minus its min size. That's the amount of space we can actually remove from the free space. Then we remove the this sizer's particular stretch factor from the total amount of stretch available for this particular set of box sizers. We set its size to its minimum size. We say that it's done, and then we subtract from some of our counters how many things, stretch counts that we have that are greater than 0 or greater than 1, and then how many sizers are not yet done. And again, all of those, where do we use the not done count? It's actually done down here. So that not done count is handled right here. So that's this first loop. So once we get through the first set of sizers, so that, again, this is a double loop. And so we enter that loop and we go through and we iterate over all the sizers. Once we go through all the sizers, we might be fine. We might have only hit all of these else clauses, and then we come back up here and the stretch count is still going to be greater than 0, but the free space is not going to be greater than or equal to near 0 because we consumed all of the space. So that's fine. So then we only entered this while loop once and we're done. However, if we hit this if clause right here, where I've tried to resize a sizer to less than its minimum size and I can't do it, then we're going to pop out of this for loop and we're going to have free space that is still greater than 0. So we enter the loop again. And that means we've taken this one particular sizer out of or maybe more than one, but let's just call it one for this case. We've taken this one particular sizer out of the pool of things we can deal with, but we still have free space left over. So we go through it again and we try to give that space to any of the other sizers that can take more. And again, we're trying to give it right now at this point only to sizers with stretch factors that are greater than or equal to 1. If we pop out of all of these loops, so the for loop's done and the while loop's done because we've either distributed all the space or all of the sizers that have a stretch count greater than or equal to 1 have hit their minimum size, which makes them done. Then we'll get down to this bottom loop down here, and we'll see that, hey, we've got some sizers that aren't done yet, and we still have free space that's left over. In that case, now we go through and we look for sizers that aren't done, which means that their stretch factor is 0, because if the sizer's not done and it had a stretch factor greater than 0, it would have been handled by this loop up here. So we know that if we get down to this point right here, its stretch factor is 0. So now we're giving whatever space is left, and we're proportioning it evenly among all the sizers that have a stretch factor of 0. And it's similar logic in terms of handling minimum sizes, etc. And then you'll see a very, very similar algorithm below it. It's the else clause. So this is point number 6 on that layout algorithm. And it's the exact same logic as up here, except it's distributing positive space rather than negative space. And so instead of minimum sizes, it's dealing with maximum sizes, if that makes sense. But should make sense, but it's literally the exact same thing. And if we get down to this point, we've allocated all the available space, and we know that the consumed space equals the available space. So we return. There's a couple more functions that I'll go over next week because we're out of time now, and there might be some questions. Hopefully there's some questions on this algorithm. I would hope, because it took me several days to write and get it correct. So it wasn't easy for me, so I'm sure it's not easy to just grok at the first telling.
Is there any notion of privileging the order in which stretch is applied from right to left instead of left to right or something like that?
No, because the computed amount will be, I guess you could, it's always done left to right. Usually it's not going to matter for the most case, because the only time that that's going to come into play is if you have some items that hit their minimum size.
Actually, maybe it wouldn't, because even if the algorithm doesn't do it, you could just pass in the sizers in reverse order yourself. So it would be like you could do it as a consumer, I guess.
No, it won't matter. And the reason it won't matter is because I think I ran into this when I was running this algorithm. And if we look, the computed amount that we're trying to change each item is only dependent on its stretch factor, whatever this dist space, so the distributed space, or the distributed stretch. And the distributed space and distributed stretch are constants for an entire iteration of this inner loop. So this is why these variables exist. It's actually a really good question, and I actually had to come back in and make these variables for that purpose. Thanks for, that actually triggered a memory. So that's why whenever I adjust a sizer, whatever the current sizer is for the loop, I'm actually adjusting the free space and the total stretch. And that is then coming up and being on the next iteration of the while loop, whatever that current value is now being basically the local value for this entire iteration. So whether I go left to right or whether I go right to left, each sizer for one pass of this inner loop is going to be, we're going to try to adjust it the same amount for whatever its given stretch factor is.
Okay, so if you, as a consumer, care about appearing to do right to left, what you should do is you should set your stretch factors to reflect that.
Yes, and what I'm saying is that, it doesn't matter. Like, if I, for example, iterated in reverse order here, it wouldn't have a visible difference on the screen.
Right. Cool, thanks.
So end of the day, this is a somewhat mentally complex algorithm, but the implementation is pretty simple. And this implementation has been micro-optimized to be as fast as possible. And it's kind of doing a lot of tricks and assumptions about how JavaScript engines implement things. And again, making sure it doesn't allocate any heap memory for any call to calc.
Maybe a question that I'm sure the answer is outside this file, but is there any kind of pruning when resize messages are going down through the tree to say, maybe you dragged the window and the left and right pane actually didn't resize, so we don't need to propagate those messages and recalculate everything inside the left and right pane? Like, is there any kind of pruning that happens like that? So
that's up to the layouts to do that, and
okay.
A lot of the built-in layouts do that, make that optimization. Yes. As a matter of fact, if we recall from this layout item class, I believe it's in the layout module. So this layout item, so this layout item is actually where that logic is handled. So if you use this layout item class and you tell it to update itself. So this is, if you're using a layout item to wrap a widget for doing layout, and you tell it to update with its new computed position, left top width height, and it detects that it hasn't been resized, then that widget will not get a resize message.